This is a video for AQA Further Pure Mathematics. This is section vectors 2.5, where we're looking at the intersection of lines in 3 dimensions. Well, when we have lines in 3 dimensions, the possibility for them are similar to 2 dimensions in that they can intersect at a single point, be parallel and not intersecting, and be parallel and collinear, in other words, exactly the same line. But there's one other possibility. You could try this with 2 rulers just to check for yourself. There's a fourth possibility, which is that the lines can be non-parallel but don't intersect. And this is what we call skew lines. The picture here shows a good example of skew lines where we have 2 motorways intersecting each other, but of course they don't going across each other rather, they don't actually intersect at a point, they are skew. So we've got 4 possibilities when we have lines in 3 dimensions. The method of solving those is very similar to that we had in 2 dimensions. So that if we've got 2 lines here and we're told that there is a point of intersection, then what we need to do is to write from these the equations of the coordinates for x, y and z and equate those. So looking at our equations, if we look at the x values, then in equation 1 we have that 2 plus lambda for L1 must be equal to -1 plus mu for L2. The y value gives us that 4 plus 0 must be equal to 2 plus mu in L2. Now we can see from that if we call these A and B, the second equation B means that mu must be equal to 2. Now that again is sufficient, but we could also go on to check that that means that lambda is equal to -1. Once we've got mu is equal to 2, because we know that the lines intersect, then we can use that. And so mu equal to 2 means that L2 gives us R is equal to -1 plus 2 in the I direction, 2 plus 2 in J, and then 1 minus 2 K. So that gives us I plus 4J and minus K, although the point of intersection is therefore 1, 4, -1. Now you could also go back and check that lambda gives the same value in L1, just to be sure that we have got our working correct. So the method is, you see, the same as when we're in 2 dimensions. We write down the equations for the coordinates and then equate those simultaneously so that we can then solve for either mu or lambda. In this example here, we are asked to find a value of alpha, again given the fact that the lines intersect. So looking at this method then, the intersection would mean that if we equate the 2 sides, for R1 and R2, we see that for R1 we have that 1 minus lambda, -1 plus 3 lambda and 2 plus 4 lambda are the values, and they must be equal to alpha for the x direction, -4 plus 3 mu in the y direction and 2 mu in the z direction. So looking at the z coordinates, we see that that means that 2 plus 4 lambda is equal to 2 mu, and therefore we get that mu is equal to 1 plus 2 lambda. We can substitute that into y, so that we have that negative 1 plus 3 lambda is equal to negative 4, beg your pardon, negative 4 plus 3 times 1 plus 2 lambda. And if we look at that, that will mean that we have a lambda must be equal to 0, so that we get negative 1 is equal to negative 4 plus 3. So lambda is equal to 0, and substituting that into the x coordinate, we get that alpha must be equal to 1. So those two examples work slightly differently to each other, but both where we knew that the lines intersect. Well, in this example, we don't know whether the lines intersect or not, so we have to determine that. What I'm going to do is to go through the method and ask you then to pause the video and try it for yourself before you look at the solution in the following slides. So if we don't know whether the lines intersect, the first thing to do is to check whether indeed they are parallel or not. If they're parallel, then they will be collinear or non-intersecting. So we can do that easily by just looking at the direction vectors of the two. What we then need to do is, as before, write down the equations given by the coordinates x, y and z, and then equate those so that we form a set of 3 simultaneous equations. We solve 2 of those equations simultaneously and get values of mu and lambda, and then using the third equation we substitute those values of lambda and mu to see whether it works for the third equation, or those values work for the third equation, in which case we found a single point of intersection, or whether in fact that leads to an inconsistency, in which case the lines will be skew lines. So that's the method. Pause the video now and work through it yourself before you look at the solution. Well, we look at the direction vectors, and we can see that for the direction vectors we've got negative 2, 0, 1 and 4, negative 2, 5. So we can say that the direction vector 1 is not a constant multiple of direction vector 2, and therefore they're non-parallel. We now write out the equations for the coordinates x, y and z, and then we need to solve those simultaneously. That gives us a value of mu is equal to negative 5 and lambda equal to 12. If you now take those values of lambda and mu and substitute them into equation 3, we find that we get something which says that 14 is equal to negative 28. Obviously that's not correct, and therefore these are inconsistent with each other, so that we have skew lines. Had the equation been correct, then we would have found a single point and we could work out the point of intersection. Well, that concludes this video looking at intersections of lines in 3 dimensions. In the next one we'll be looking at perpendicular distance of a point from a line.